In this video, I want to talk more about normal subgroups and how they're related to cosets. Let's start by reminding ourselves what a normal subgroup is. Let's start by letting H be a subgroup of G. We say H is a normal subgroup of G if for any element A in H and any element X in G, we have that XAX inverse is still in H. Using this definition of a normal subgroup is kind of cumbersome. For every single element A and H and every single element X and G, we would need to check this multiplication. So if we have a rather large group, this can be particularly difficult. So let's try to find a better way to test if a subgroup is normal. If H is a normal subgroup of G, then the left coset AH is equal to the right coset HA for every element A and G. In other words, for a normal subgroup, there's no distinction between left and right cosets. So let's see if we can prove this. Let's start with an element X in AH. Then, by definition of the left coset, X is of the form AH, where this is some little h in capital H. Since we're assuming H is a normal subgroup, we know that it's closed under conjugates, so we know that AHA inverse must be in H. So we have that X is equal to AH, which is the same thing as AH A inverse A, because multiplying by A inverse A is just the identity. So this is regrouping. We know that AHA inverse is an element of H because we just noticed that it was closed under conjugates. So this is of the form H1A, which must be in the right coset HA. So what we've shown now is that AH must be a subgroup of HA, provided H is a normal subgroup. And similarly, we can get the other way. We could get HA as a subgroup of AH, which would then show that they are equal. This doesn't tell us that just because the left and the right cosets are equal, that means it's a normal subgroup. But if we can show that the left and right cosets are different, we know it's not a normal subgroup. The next thing I want to look at is coset multiplication. Let's let G be a group and H be a subgroup. So I can look at a coset HA, and I can look at a coset HB, and I can actually multiply these cosets, and I'm going to define this as HAB. Let's look at this definition of multiplication of cosets a little more in depth and see if this is a valid way to define multiplication. As an example, let's let G be S3 and H be the group generated by 1 and 2, 3. Let's find H of 1, 3, 2. Well, we take an element of H, the first one's the identity, and compose it with 1, 3, 2. The identity composed with 1, 3, 2 is 1, 3, 2. The second element of H is 2, 3, composed with 1, 3, 2. 1 goes to 3, and 3 goes to 2, so 1 goes to 2. 2 goes to 1, and 1 stays the same. 3 goes to 2, and 2 goes to 3. So the second element is 1, 2. So that tells me this is also the coset H, 1, 2. Next, let's find H of 1, 2, 3. The identity composed with 1, 2, 3 is just 1, 2, 3. The element 2, 3 composed with 1, 2, 3. Well, 1 goes to 2, and 2 goes to 3, so 1 goes to 3. 3 goes to 1, and 1 stays the same. 2 goes to 3, and 3 goes to 2, so the other element is 1, 3. So this is also the coset H, 1, 3. The next thing I want to look at is 1, 3, 2, 1, 2, 3. So I'm essentially wanting to talk about the multiplication of these two cosets. Well, the first element would be the identity, composed with 1, 3, 2, 1, 2, 3. In this case, we have 1 maps to 2 and 2 maps to 1, so 1 maps to 1. 2 maps to 3 and 3 maps to 2, so 2 maps to 2. 3 maps to 1 and 1 maps to 3, so 3 maps to 3. So here I just get the identity. The second element of H is 2, 3, composed with 1, 3, 2, 1, 2, 3. 1 maps to 2 and 2 maps to 1, so 1 maps to 1. 2 maps to 3, 3 maps to 2 and 2 maps to 3, so 2 maps to 3. 3 maps to 1, 1 maps to 3, and 3 maps to 2, so 3 maps to 2. So this gets us back to H. Finally, I want to look at H 1, 2, 1, 3. The first element is just the identity, 1, 2, 1, 3. In this case, 1 maps to 3. 3 maps to 1 and 1 maps to 2. 2 maps to 1, so we have 1, 3, 2. The next element of H is 2, 3, composed with 1, 2, 1, 3. 1 maps to 3 and 3 maps to 2, so 1 maps to 2. 2 maps to 1, and then 3 maps to 1, 1 maps to 2, and 2 maps to 3, so the other element is 1, 2. So the purpose of this, here I multiplied two things, and I got their product. However, at the same time, I multiplied those same two things and got a different product. And this is a problem, since for an operation, this solution needs to be unique, and it was not unique here. This is not a well-defined operation. How I represent the coset would change my solution. So this is actually not a valid operation. This is not a valid way to define multiplication of cosets of subgroups. However, it does work and it is perfectly valid if H is a normal subgroup. So the next thing I want to do is show that this does work if H is normal. So what I want to show, we're going to let H be a normal subgroup of G. If HA is equal to HC and HB is equal to HD, then HAB is equal to HCD. Essentially, I want to show this definition of multiplication is well defined if H is a normal subgroup. If we have that HA is equal to HC, one of the elements of every subgroup is always the identity. So that tells me that A is in HA, so it must also be in HC. So that tells me that we can write A as H1C, where H1 is in my normal subgroup H. Similarly, since HB is equal to HD, then we can get that B is equal to H2D. This tells me that AB is H1C times H2D. We do have the associative property, so I'm going to write this as H1 CH2D. Since we know that CH2 has to be in CH since it's of the form C times an element of H, and we know that since H is normal, CH is equal to HC, we know we can also write it as an element in H times C, so we can also write it as H3C. So now we have that AB is equal to H1 times H3C D. Regrouping, I have an element in H times CD, which then tells me that AB belongs to HCD. And we've already proven that if this element belongs to HCD, then that means HAB must be equal to HCD. This is something we proved in a previous video when we first started talking about cosets.